Hi class, this week we're going to work on Boyle's Law. This is not a difficult lab at all. However, it's time consuming and you're going to be dealing with a lot of numbers, some of them very large and negative numbers. And if you mess up on one number, it affects everything else that you do. So take your time on doing this lab. These are objectives of the labs. We're going to jump into Boyle's Law. Boyle's Law, by now you should already understand Boyle's Law or learning Boyle's Law. And Boyle's Law has to do with the relationship between pressure and volume. It is inversely proportional, which means when one goes up, the other goes down. So if we look here, we have 1, that's your initial conditions. 2 is your final conditions. And if we take a look at this picture here, volume 1 is 4 liters. The initial pressure is 1 atm. But when we look at the final conditions, we have the volume has decreased from 4 to 2, so we expect the pressure to go up from 1 to 2, and it does. So this is the inverse proportional relationship. The amount of gas, so the N, the moles, is held constant, and also is the temperature. So we do not work those into this because they are constant, they stay stable. In this experiment, I'm going to cover more detail about this experiment because if I don't, this lab is going to be extremely confusing to understand. And I'm hoping with more detail, it makes more sense on why you're doing the calculations that you're doing. So we're going to use, or they used in the lab in your reading, a simple syringe. And the syringe is going to increase or decrease in volume inside the syringe by placing weights on a wire loop attached to the plunger of the syringe. And by increasing or decreasing the volume, we expect the pressure to inversely, since there's a relationship, we expect it to either go up or down based on whether the volume went up or down. One thing I want to point out, they use PATM. Normally when I see this means that the units are ATM. Not in this case. They use this PATM, as atmospheric pressure. You are going to be given atmospheric pressure in inches mercury, and you'll need to convert them to pascals. And pascals is a very large number, so this is why we start dealing with larger and larger numbers in our calculations. Lab flow is interesting because these are the pictures they give in your PDF. They're not very clear at all. They're kind of fuzzy and they're very small. I found these online, so they give a better idea of this lab. So there's 2 parts to this lab. You're going to be given data points, volume. You're going to be given the volume, and you're going to be given the masses of the weights. The first portion is here where it's going to decrease the volume, and you're going to have the weights that have along with the volume that's been decreased. Second portion, syringe is going to be flipped, and you're going to increase the volume, and you're going to be given the weights that lead to the volumes being increased. So here's the first part. You're going to, the lab was started with 5 mils inside the syringe, and the pigtail, which is this nice little part here, which they don't really give a great picture of, is approximately 1 mil in there as well. So the total air inside this sealed or closed syringe is 6 mils of air. From there, weights are going to start being added, and you're going to see that you're going to write down the changes and then calculate everything that needs to happen here. So the syringe is not open to air, so the moles stay constant. The temperature is given to you before and after, and that also should not change for Boyle's Law. So we're decreasing the volume here, and you're going to be given more and more weights in your measurements on this one. The second part, syringe is flipped, and it's going to increase the volume, and then the weights are also going to be given to you. And you also start out with 5 mils inside of air and 1 mil in the pigtail. So I need to explain the pressure. So the pressure inside the syringe is eventually not going to be the same as the atmospheric pressure. The first reading, since it's initial, we have not started, the air inside the syringe is going to match the air outside. So the atmospheric pressure is going to be equal inside the syringe and outside. But the minute we start putting weights onto the syringe is going to change. So we have to account for that change. So the pressure is the area times the force. So the force is the syringe pushing down or pulling up on it, and the area is the plunger itself. So we're going to take the circle part as the area. So pressure is force over area. For this slide, we're focusing on area. Next slide will be force. The area is area times pi times radius squared. You can see right here what that is. It's the area for a circle, and they give you the answer in your PDF. And this number is going to come back in column E when we're trying to determine the force the pressure of the plunger. And it changes for every reading because we're using different weights. So area is taken care of in this slide. I'm explaining where area is, and it's given to you. So you don't have to do any of the math on that. That's nice. Force is going to change with every reading because the force, like I said, the force is pushing down or pulling up on a certain amount of area. That force is the weight. So if we break down force more, force is mass times acceleration. Mass is going to change for every reading. Acceleration is gravity. So we are going to have a different m for every reading, and you're going to multiply it by 9.8, and that's going to give us the force. And then the next column, we are going to determine the pressure, since we'll have both of these values. That's in column E. This is all explained in your PDF. So if you're not understanding something I'm writing here, make sure you should absolutely be reading your PDF way before you even touch any of this stuff. Now, because we're doing 2 portions of the lab with the syringe up and the syringe down, your reading tells you, and there's only one column that you'll have to actually do values different than the first part of the experiment, and I'll cover that. So what I mean is that we are adding the syringe pressure with the atmospheric pressure, and then when we flip the syringe, you actually have to subtract the atmospheric pressure from the syringe pressure. And if you don't catch that, you will do that portion of the lab wrong, and those values depend on everything else in that chart. Now we are dealing with atmospheric pressure. So what is our atmospheric pressure? In here we're dealing with pascals. I was given 30.08 inches mercury, so I converted it. Here's your conversion. That's what you see here. Now, if you multiply this, it gives you 3386.39, and that's the number. So honestly, if you just take your inches mercury and multiply it by this, it gives you your pascals. This is a very large number. So we're already starting out with large numbers, and they get larger. So do not panic when you start seeing that you're dealing with very large numbers. But dealing with very large numbers means you really increase your chance of messing up your values and not having any idea which value is wrong. So make sure you take your time on this. Okay, so you're going to see this in column F. It's going to come back to you. This is a PDF. This is your PDF and a chart. Your PDF shows you how to break down each step. LabFlow, when you enter your data, does not. So I'm going to break this down for you. A is the data volume that you're given. You're given A and C. So you're given this. All you do is add 1 mil for the pigtail. So all these values here, pretty easy. Your mass will start out with 0, and then you'll be given masses here. D is force times mass times acceleration. This is your mass. You're multiplying by the gravity, and you're solving for the force. Once you solve for the force, you're solving for force over area. So you're getting the pressure of the syringe. It doesn't say pressure of your syringe, but that's what this column is. It's the pressure of your syringe. It says it right here. Now you're on F, and now you're taking the pressure total, which is the pressure of the syringe plus the pressure of the atmosphere. Keep in mind that I have 2 values that you need to do here. Y, I'm going to cover that in the next slide. And then G, you have pressure times volume, and that is column B times column F, and you put them down. This is where you're going to start getting very, very large numbers and negative numbers on these last 2 portions here. Okay, so these are my readings for 1, 2, and 8. I'm going to give you an example of how to do this. So you can see here I have my volumes. These were given to me. I just added 1 on all of them. My first reading, I started out with no mass, no weights, and then I was given weights, and then completed these. So this is what I started out with. Now I completed these. I'm breaking this down again. So let's look at the initial. The initial is 5, so I added 6. I had no mass added, so it's 0. So 0 times 9.81 is 0. 0 divided by a number is 0. And then here's that number I was talking about. Here is my atmospheric pressure. That was right there. So that's the line. That's what you're going to write there. If you got my matching 30.08, you're going to add that number there. Let me skip one. And then you're going to take column B and F and add them together, and that's what you're going to get here. Now, I'm not going to do 2, but I'm going to jump to 8. So I have a volume of 6.3, so I have a volume total of 7.3. My mass is 0.35, so I took that, times it by 9.81. I got this number here. I took that and divided that number by the area of the plunger, and that gave me a number here. Now, I want to jump down here. This is from your PDF. It says that when you invert the syringe and add weights, the volume will increase from 6 mils to something greater. So the pressure ATM will be subtracted from the pressure inside the syringe. So instead of having this plus, this should be a subtraction, and you should start subtracting numbers when the second part of the syringe starts showing an increase of greater than 6 mils. So you should pay attention to your readings on these portions here. I took it from this one and not this one, but and it seemed to be fine. So once I started seeing larger numbers, I took those numbers when it was above 6 and plugged it in. So make sure you do that, because if you mess up this goes up to 11, so you're going to mess up these last 2 columns, and you're going to take some of the values here and put it into another chart, and those numbers are not going to be right. So make sure you follow the steps and thoroughly read your PDF to make sure you understand what you have to do. Okay, so here is the end of the chart. You're going to add all these together, and you're going to get the average, and average is also fancy word is mean. When you come into chemistry, you guys are expected to have a certain amount of algebra covered. And if you do not, most of the time students get upset about chemistry. It's not usually ever the chemistry you're upset at, it's the algebra. Because the algebra is very hard. And most people don't remember the algebra, and that's okay. But you have to make an active effort to review that if you're stuck on something, and understand the difference between, is it chemistry you're having a problem with, or is it the algebra you're having a problem with. And once you can figure that out, it leads you to the next step. So here you're going to take add up all the column, this is column G, add everything up in column G, divide it by the number of measurements, and that is going to give you your average number here. And this tells you add up all 11, so it tells you to add 11 here. So you're going to divide this by 11. Now the PV value, that's G, so you're going to take the next table, and this is from PDF, you're going to add all those values into the PV value. If you need more help under standard deviation, this is breaking down the steps more in your PDF. I'm also going to break it down for you, but here's the chart and what it looks like. So if you jump onto LabFlow, you actually see those parts matched up here. So you're going to take your PV values, that's G, and you're going to add them all in here. You're going to take that mean value, which is this value at the very end, and you're going to subtract that from all your PV values. So that's what it means. PV value minus mean. You're going to add all those, you're going to subtract it and put all those numbers here. Now you're going to take that answer from this, and you're going to square it in the next column. Everything's going to get squared in this next column. All you're doing is you're doing standard deviation, but they're breaking it down in steps so that it's not one step. You know, you just don't plug a number in case you didn't know how to do standard deviation. This is breaking it down. If you have to use scientific notation, I had to. This is one of my values, and this is exactly how I wrote it. I wrote the value out, a space, times, space, 10, space, exponent. And I kind of worded it out here so you can see. If and this was marked right. So I was able to, with the spaces, it took it. If you don't put a space here, it's going to think it's a very large number that's over 1,000. But so make sure there's a space right here, okay? Now we're continuing on. You're going to sum the square deviations. So what it means is that you're going to take all these numbers that are here and you're going to add them all together. You're going to enter that number into question 3. Now with 3, you're going to go to 4, and that means you're going to divide that number, and it's either n minus 1 or 11 minus 1, which is 10. So now we're on this step here. So we finished this one up here, we're on this step. So you're going to divide that number by 10. And when you do that, after you do that, you're going to enter that number, then go to 5, and you're going to put the square root. And once you do, that is your standard deviation. Your standard deviation is number 5 after it's been squared. Use the square root of it. Excuse me, not squared, but square root. 6, you're going to take a range. So you're going to take that mean PV, which is here, that number that you had here. That's the average. And you're going to subtract the standard deviation, which is number 5, from that average number, and then you're going to enter the max range, which you're going to take that number and add the standard deviation and enter that number. And that is the range of between the average and the standard deviation of how far out from the average should be. Okay, this is the whole lab. It's a little time consuming. You can see how we're one chart, you take those values and you take it to the other chart. So if something's wrong, you'll probably have to go through the whole thing again to figure out where you're wrong. It's very time consuming. It's a simple lab, but one digit wrong messes everything up. It could be. I did not follow sig figs. If you see my numbers, I just went straight through with what the calculator gave me and it marked everything right. So I don't think there's a limit on sig figs. I would suggest not to use 2 or 3 or 4. I would go, I gave what it gave to me on here. So these are accepted. But once you start getting to the bigger numbers, I tried to just keep them as big as the number that we started with. Now here is, you're going to have some questions on accuracy and precision. So accuracy is different than precision. So when we're in lab in person, I do a lab that students, once they turn in the report, they think they got it right because you do 3 trials and each trial came up with the same value. So you think that you're right because that's what the value, how could you do 3 trials and get the same number? But that doesn't necessarily mean right. You might have done something wrong each time and didn't catch it, and that's why your values. That's precision. You had the closest set of numbers closest to each other, but they were far off from the real value. So a bullseye is a good way of explaining this. The bullseye, think of this, the center as the actual answer of something. This, if you see all these data points, this is an experiment where everything is all over the place. So you have low accuracy and low precision. You're just all over. This one here is what a student in my lab would do. They're far from the actual answer, but every trial was very similar in numbers. So you have low accuracy but high precision. And then here you have high accuracy where they're all very close to the bullseye, and low precision because they're not all close to each other. They're all spread out. High accuracy and high precision. So this one is all 3 trials had very similar answers and they were all very, very close to the actual answer. So this is the difference between accuracy and precision. Accuracy is closest to the actual answer. Precision is how close a set of numbers or measurements are close to each other. Okay, so I want to explain standard deviation a little bit. I'm not going to go great detail with this, but enough to help you with this lab. The smaller a standard deviation value, the better. It gives you better precision of your measurements. They're closest to the average. So if I jump here, we have an average number. So that's the average that we were working on. And then we have standard deviations. And the further you go out, the further you are away from the average. So you want a smaller number because the smaller number will keep you closer to the average, going either way. That's what the maximum min that we were doing here is. How far out are you and how close to the average you are. So it's not, so we take the average here and we're adding, we're doing the max value and the min value. So it's considered better precision, and we use standard deviation to determine the precision. Now, in order to precision, it's the closest among a set of measurements. You need more measurements. The more measurements you have, the better to determine your precision. Usually 10 is the best. If you have less than 10, you're not going to get something accurate at all. And if you don't have enough measurements, you probably could have high precision, but it's not accurate because you didn't have enough measurements to make sure that you have high precision. Even if it's telling you that, you need way more measurements in order to determine that. So here's a problem you may get, something very similar to this. A student completed an experiment with an average mean of 5.1. That's what we used in our experiment. They're giving you the standard deviation of 0.76 mils. It's asking for the max and mil range within 1. So this is a 1 and this is a negative 1. So they are asking for something that's based here and not with a 2. I'm not going to explain these more than that, but here's a 1, here's a 1. So this number here falls within this 1. So what is the minimum max value within 1 standard deviation range? So here, I am sorry if you can hear my son screaming outside. So you take the average value, which is here, and then you're going to plug in the 0.76 and you're going to add it. And you're going to subtract it for the minimum, and that's 4.3 is the minimum value. And the maximum value is 5.9. So that's the max and the min from the average away from this that you want to be for 1 standard deviation range. You may get a problem that's very similar to this. You can reflect on this problem here and to be able to answer it. By the way, I didn't answer any units on anything. For the lab part or the quiz, I never answer units, and they're always marked right. So you may get another question, and this question has to do with newtons. This is more of a physics problem because In my chemistry, we do not ever touch newtons, so I'm a little annoyed by this. Yes, I'm sure in some chemistries they probably do, and I did have to learn it, but in my experiments, we just don't touch it. But I'm going to give this to you so you understand. 1 Pascal is 1 Newton over meter squared. So you may get a question that is asking a force of 22.0 newtons is exerted over an area of 0.00226 meters squared. Now remember, force over area, so it's pressure. I forgot to put, so pressure is force over area. So force over area, and it gives you the pressure. And I followed sig figs. I did follow sig fig rules for quizzes. I don't know if I said that. I don't ever enter units for either. And for this lab, I really was kind of carefree about sig figs on the data report side, but I definitely followed sig figs for the quiz. So you should definitely try to do that. And follow the sig figs. There's three, so my answer is in 3. I put pascals here, but when I entered a problem that's similar to this on the quiz, I didn't enter any units. Okay, so this lab, you may have very large numbers, and you will. You may have negative numbers. You may have negative large numbers. If you need to use scientific notation, I told you how to break that down. Take your time. 1 row wrong is going to mess up everything else because it's all intertwined. So take your time by doing this. Did not enter units for my answers in my quiz or my lab portions. Okay? And that's it.